Hello everyone, welcome back. Today we are going to go over electrophilic aromatic substitution. Alright, so what is EAS? So EAS essentially it proceeds through a two-step mechanism as always. This is like a general, sorry, let me switch colors. This is a general type of um, template for this kind of reaction. So first you have the aromatic ring acts as a nucleophile. So if you remember, nucleophiles like attacking electrophiles. They are the source of electrons. This forms a carbocation intermediate and it temporarily breaks aromaticity. So we break this aromaticity, but then we reform it right after because we deprotonate a CH bond to regain it. So hopefully that makes sense. So we start out with this hydrogen here, and at the end we lose it to form whatever E is. So let's simplify it again. We have an attack of an electrophile by this aromatic pi bond, and then you have deprotonation that results from the hydrogen that's attached to the same carbon as our electrophile. And at the end, we have this is our final product. So alone, this really won't react, or if it will, you'd need a very powerful electrophile. Generally, benzene on itself doesn't just grab electrophiles like that. But so we have to make these electrophiles more attractive. But we will come back to that in a minute. First, a separate small segue into what an EDG and an EWG is. So EDGs are known as donating groups, and EWGs are electron withdrawing groups. So EDGs, they increase the rate of reaction. They basically pump electron density into the system. So EDGs are good. And EWGs, they decrease the rate of reaction. So they're bad in the sense of reaction rate, good versus bad. And you also need to know these positions here on the ring. So you have ortho, meta, para, meta, ortho. And this is all relative to this R group. All right, so what are ortho and para directors? So you got to remember two things. These directors are EDGs and halogens. This will result in the incoming group, right? It's going to attach either ortho or para to the group already on the ring. So remember, it's all relative to the group on the ring. So ortho-para directors, they include your hydroxyl, your alkoxy, your amino, your alkyl, and your thio, and your halogens. However, these guys are considered the activating groups, which we'll get into in a minute, and these guys are considered the deactivating groups. And so here you could see all of these guys are your ortho-para directors. Hopefully that makes sense. So let's note. So para is generally more favored, particularly when there's significant steric hindrance with the group on the ring. All right. So isopropyl or larger. So if you have an isopropyl group, right, like this guy, even though it's an activating group, it's mostly gonna form only para and not both ortho-para, just because of this steric hindrance if it's in the ortho position. However, when you have a methyl group, it doesn't matter. Statistically speaking, you're going to get a fairly equal mixture of the two. So now we want to go into why does this happen. So it's basically with the intermediate carbocations, they are stabilized, right, in the ortho-para position when you have an electron donating group. So after this electron donating group, here's the electron donating group right here. You have your methoxy group, okay? So it's going to attack this electrophile. And if you could perform resonance, you could see we can get this particularly stable resonance structure where we have every single atom having a full octet. Even though oxygen has a formal charge, right, of 1, that's completely fine. The important thing is that every single atom has a full octet, and that is what we care about. That is a very stabilizing effect. So that is why ortho is favored as a position relative to electron donating groups. Now let's look at para. Same thing goes for para. So you can do resonance, and we can show that this is the favorable, stable resonance form, right? Where all atoms have full octets. So if you need, take a minute, look at these resonance structures, but this explains why we care so much about ortho and para? Why isn't it like ortho, para, meta? Why does it matter? This is why it matters. Now the question, obviously the next question is, why don't we form meta? The meta product is not formed by activators and halogens because you would basically lead to unstable resonance forms. So this is basically the worst uh, choice. You're not going to get any resonance structure here that has a full octet. So in each case, you have an atom like a full octet, and you don't want that. That's why we don't form meta. So halogens, remember, we talked about them being deactivating groups. They can somehow stabilize adjacent carbocations. How? Well, they can act as pi donors. So I know that it's a little confusing because we've talked about halogens acting as electron withdrawing groups in Orgo 1 when we're talking about instead of stabilizing a negative charge because they pull charge away. However, this sort of resonance effect triumphs that sort of electron withdrawing effect that we talked about. Okay, so pretty much halogens, they do weakly stabilize, but they do still stabilize carbocation, and that's why they are they're deactivating groups that act as electron donating groups. Hopefully that makes sense. All right, let's talk about meta directors and ring deactivation. Two things to remember. Meta directors, they're your electron withdrawing groups. They're also known as your deactivators. An electron withdrawing group on a benzene, right, it deactivates the ring. You cannot add deactivating groups onto an already deactivated ring, but this is a general statement. So this statement doesn't apply to every single case. We'll talk about this later, but this means that you can't add, for example, a nitro group, and then add a, I don't know, acylation. You can't do that. However, you can do the reverse. And the reason is because the nitro group is very deactivating, and the acyl group not so much. But we will talk about this later. So this statement is just a broad statement. So a deactivated ring, you don't want to deactivate your ring too much if you want to continue adding things to it. So why does this happen? So let's look at CF3, right? So basically 3 fluorines as a meta director. This is a great meta director. So if you look at these 3 resonance structures, right? In all cases, one atom does not have a full octet. All right? And so even this is considered a very minor resonance contributor. Okay? This is in the ortho product. You can see this is not a stable product. In the para product, same thing. No stabilization in this case. However, we get to the meta product. The metacarbocation is more stable than either ortho or para. Basically, it's not stabilizing the intermediate, but it's less unstable. That's what it means. It's less unstable because the carbocation is here, here, and here, rather than on one. Yeah, on one. So that's pretty much it. So that's why the meta substituent, we try to make this clear. It does not stabilize the meta intermediate. It's just a less unstable than the ortho and para intermediates for this group. Hopefully that makes sense. All right, let's get into our reactions. So reaction 1, halogenation of benzene. So if you recall alkenes, they readily react, right, with chlorine and bromine. However, EAS disrupts aromaticity. So that means we need to give the aromatic system a boost, right? This is a really unfavorable reaction to just attack with chlorine and only chlorine, right? Like not attack, but use chlorine as electrophile and only chlorine. But we need to give this benzene a better reason to do it. Basically change the free energy, make it more favorable. Now, how do we do this? We do this by using Lewis acids. So Lewis acids, such as powerful Lewis acids such as aluminum trichloride, or I would just call it aluminum chloride or iron chloride. Okay? So note, using a Lewis acid is not enough to make iodine an active enough electrophile. So there's a separate reaction for that we can cover in the future. But essentially what you're going to do is you're using some sort of halogen, so chlorine or bromine, and you're using either iron or aluminum chloride, and you essentially replace one of the hydrogens on the ring with that halogen. Let's look over the mechanism. So the mechanism is, as previously stated, with three parts, right? So the first part is we're going to prepare our Lewis acid. The bromine essentially attacks this iron atom in the center, and you form this kind of complex right here, right? Where you have this negative charge here, positive charge here, and this delta P here. Then your ring attacks this bromine, these electrons get kicked back, this bromine, and you get this carbocation intermediate. And at the end, you get this deprotonation by this original bromine here, and you form HBr, FeBr3. So let's go through that again. First, you get the activation of this complex right here. Then you get the attack of the electrophile with this benzene ring grabbing this bromine. And at the end, you get this deprotonation to reform the aromaticity. So this is pretty much a general mechanism for every single reaction that we're going to cover today. All right, this is an important reaction. It's called Friedel-Crafts alkylation. So it allows us to add carbons to a benzene ring. So you got to note there's some limitations. Rx, so whatever alkyl group you're using, it needs to be an alkyl halide, right? You cannot use this. Don't use that. You can use this, okay? You may get carbocation rearrangement. That is very important. It works poorly with already deactivated rings, and you want to avoid using it for synthesis. You can. So essentially what you're doing is you're adding an R group on your ring, and you're using AlCl3 and this R group. So hopefully that makes sense. Let's look into how this works. So the mechanism is as follows. First, this chlorine that's going to be attached to your alkyl chloride or whatever is going to attack your aluminum, and you're going to get this activated electrophile. So at this point, it's common for the chlorine to dissociate, and you can form this kind of carbocation here, the weakly associated chlorine, and this is where your carbocation rearrangement can occur. So you have to be careful. This is the point where it could occur. Then your attack of your electrophile is going to occur here. Same kind of principle, and you're going to form this complex right here. And finally, you're just going to deprotonate. Last step, deprotonation. And you form hydrochloric acid. You form your original reactant, starting product reactant, and you get this beautiful benzene with an isopropyl group. Hopefully that's good. So let's do the first practice problem together. Draw the major product from the following reaction. All right, so hopefully you understand that this is basically just halogenation. So we can put on any of the six, doesn't matter, it's going to be the same product. Let's do this problem together. Let's draw the major product from the following reaction. So you might be tempted to simply just disconnect this and just connect this carbon to any carbon on the benzene, but I would not do that. Why? Because we talked about that there's a possibility for carbocation rearrangement. So first, let's form our carbocation. How is it going to look like? Well, it's attached to this carbon, so the carbocation forms there. Well, we can have a hydride shift, and this hydride shift lets us form a stable tertiary carbocation. And from there, so this is the carbon that I'm connected to two more. So 1, 2, 3. 1, 2, 3. Hopefully that makes sense, but you need to be careful. There could be rearrangements. So let's do this. Draw the major product from the following reaction. Take a second. Okay. Well, I kind of set this up in a way so that you might be thinking, well, it's already attached onto this alkyl group here, so I'm probably going to get another ring. Well, if you thought that, then you thought correctly. So this is the part where I would count. So number 1, 2, 3, 4, 5, and 6. So if I'm just going to start out drawing my 6-membered ring like so, very important that I get the numbering right. This is 1, 2, 3, 4, 5, 6. Don't forget this guy here, attached to 6. And that's my final product. Hopefully that makes sense. So this can be very useful to making systems like this. All right, next. Friedel-Crafts acylation, the bigger and better brother of Friedel-Crafts alkylation. Right. So essentially here we start with a benzene, and we use this sort of acyl chloride. So you got this your carbonyl right here attached right next to a chlorine and an R group, and you use acyl3, and you get this great group here. So this is an extremely useful reaction. No carbocation rearrangements. That's amazing. So use it for synthesis. However, it fails in strongly deactivated rings. So what are strongly deactivated rings? Well, probably 2 nitros or more. But we'll talk about that even later. You can also use anhydrides, which we'll talk about in the slide after this mechanism. So how does this work? Well, this activation of electrophile, once again, this is the first thing that happens. This chlorine grabs aluminum, then you're gonna get this carbocation that forms like so, and the carbocation is gonna be stabilized by the pi electrons in the oxygen, form this acylium ion. You know, they're supposed to know the name. And then the acylium ion is an amazing electrophile, and the benzene is going to attack the acylium ion, and you're going to form uh, this sort of acyl group. So basically, acyl chloride, the chloride leaves and is gone. And the final step is deprotonation, as usual. Hopefully, you're seeing a pattern here. All right, so you can also do Friedel-Crafts acylation with anhydride. So this is what an anhydride is. This is the basic form of an anhydride. And we also even have the mechanism on the following slide. But pretty much, you're just going to chop off this part and attach this group onto the any of the carbons. And the same thing goes for this, except if you're going to chop this group off, so you're going to attach this group to this carbon, and yeah, and so you're going to count from there. So this is 1, 1, 2, 3, 4, 5, 2, 3. Technically, if you're astute here and you realize, oh, I need an acid workup, you would be right. You would need an acid workup. However, we don't really need to write that. By what I mean by acid workup is where did this hydrogen come from at the end? So that would be through an acid workup because you just have it attached to AlCl3. But we'll show it in the following slide. And so the mechanism is nearly identical. You're going to form this activated electrophile right here. Then you're going to have this attack of the electrophile with the benzene ring, form this kind of complex, and that complex is going to attack, and you're going to get this molecule. And then deprotonate once again, and acid workup at the end. But you don't acid workup. I mean, I'm not sure. Depending on how strict your professor is, you may or may not need to draw that. But the mechanism is generally the same. All right, Clemmensen reduction. So a Clemmensen reduction, what is this? It can be performed after acylation. So you can basically get rid of the carbonyl. All right, it's very useful because you can convert a deactivating group into an activating group. It does not work in carboxylic acids though, only with benzylic/aromatic carbonyls. Okay? Don't use it with a protecting group on it because it's performed in highly acidic conditions, and we'll show you in the next few slides why you'd want to do that. But just don't use a protecting group, right? Don't have a protecting group on and then do this because it's going to remove your protecting group as well. And this can also work on esters. All right, nitration. We can nitrate benzene pretty much the exact same way. However, you got to be careful that further attack after nitrating might not be the best idea because the ring is pretty deactivated at that point. So if you have a synthesis where you nitrate and then you think you might need to acylate after, try doing it a different way because that might cause you to either run into some problems or your reaction rate's going to be way too slow. All right, let's look at the nitration mechanism. So first we have the activation of the electrophile as always, right? You have nitric acid, HNO3, it's going to attack your sulfuric acid, and it's going to create this nitronium ion. That is the first step. Then your electrophile is going to be attacked by the aromatic ring, and you're going to form this complex here, and finally you're going to deprotonate to get this beautiful nitrobenzene group here. Hopefully that's clear. So from our nitrated benzene, this is extremely useful reaction. We can actually turn a nitrate into an amine. Very helpful if you need to turn a deactivating group into a strong activating group. And it's a very simple reaction. All you do is just apply H2 over palladium. Sulfonation, this is very useful as well. We can add a sulfo group and we can use it to block positions on the benzene ring that we don't want to occupy. So this is kind of used on its in conjunction with other types of reactions in order to get let's say if you only want something in the ortho position, this is what you would use, and this is completely reversible. That's the most important part, that this is reversible. But you don't want to use, don't do like your zinc amalgam, don't do your Clemmensen reduction, and then like don't do your sulfonation, and then your Clemmensen reduction. Don't do that, because after that, you're gonna take off the protecting group because this has HCl in it. So that's gonna cause your protecting group to leave if you do that. So I would not risk it at all. All right, let's do a sulfonation mechanism quickly. So you have this beautiful sulfur trioxide, and it's going to be activated through this protonation. You're going to get this beautiful activated electrophile. Once again, the benzene's going to attack. You're going to form this complex, and you're going to deprotonate to restore aromaticity. Not sure if that's a mechanism you need to know, but it's always nice to have. All right, so here's some general tips. So positions that are promoted by both electron donor and electron withdrawing groups on the benzene are the best. So this is not a direct example, but I can draw a good example here. So let's say you have an NO2, and so NO2 is going to promote here and here. This is meta. And if you have a chlorine here, well, this is a reinforced position right here. This is the best position for anything to go on, because the chlorine is going to promote ortho and NO2 is going to promote meta. The stronger activator wins. So in this case, chlorine is the stronger activator than NO2. So you would get your group here, para, or you can get here and here. It's hard to predict the exact outcome, but either or. And sterics are important. So para might be more favorable if there are bulky carbon groups already on the ring. However, in this case, this is just an example for the strongest activator. This NH2 is the stronger activator, so you will get R here and R here. Once again, this goes back to the previous few slides. All right, hopefully these tips make sense. Let's continue. All right, so this methyl group is an weakly activating group. So it's going to promote ortho and para. So you're going to get your ortho product, you're going to get your para product. Kind of hard to predict which one in this case, but you would be getting ortho and para. All right, let's do this problem together. Give you guys a second. Okay, so as we know, this is going to add a sulfur group. So I'm going to add it here. Okay, great. Now, is this a weakly deactivating or weakly activating? This is a weakly deactivating. So weakly deactivating is going to be in the meta position. We're going to put our chlorine here. Our final answer should look like so. Oh, no. Chlorine should be here in the meta position. Did that make sense? Let's continue. Let's do this one. This is basically the reverse. Okay. So this, hopefully at this point, you know that is going to add simply just going to add a chlorine on any one of the positions on benzene. And because this is a weakly activating group, it's going to promote either ortho or there. Hopefully that makes sense. Continue. All right, guys, let's do this one together. So you can sit here and try the mechanism. That's one way to do this. Another way to do this problem is you can try using a shortcut. So I like shortcuts, but I also like understanding the mechanism. That's why I gave you guys the mechanism. So what can I do here? Well, I know that I'm going to experience an attack here or here. It's symmetrical, but either or. So if I experience attack here, I'm going to start numbering 1, 2, 3, 4. Okay? So if I'm experiencing an attack at 1, this is 1, this is 2, this is 3, and this is 4. 4 is connected to my bromine and the CH3. So I hope you understand we experience attack at 1 because that's the one attached to the bromine. And if you don't understand, please go back to the previous slides for the mechanism. And then finally here, this is after the deprotonation step, we can perform another Friedel-Crafts alkylation like so. And our final product, we're going to have our benzene ring with a 6th membered ring, 1 carbon off the side. So just to keep our numbering consistent, 1, 2, 3, 4. This is 5. Oh, and we have a methyl on 1 as well. Not forget those. So I'm going to erase this. Get this as our final answer. So 1, 2, 3, 4. This could be 5. And this could be A, just to not be confusing. So A and 5. Hopefully that makes sense. Let's continue. All right, so this one takes a few steps, but let's do this one by one. So the first step, what are we doing? Well, we are nitrating the ring. So we're going to add a nitro group. Then we're adding a blocking group. So SO3H. Where would SO3H go? It's going to go in the meta position. Which meta position doesn't matter. So let's put it here. Now we're going to do our Friedel crafts, right? Chlorine's going to go here. And then finally, we're going to apply H2 PDC. So what's that going to do? It's going to get rid of this group. So our final answer, we're going to have the chlorine. It's going to be meta to the NH2. And this sulfur group is also going to be meta. Hopefully that makes sense. So I think the easiest way to do these is just go one by one. One by one, and just add things onto the benzene. And you got to keep these rules in mind. All right, let's do this. So what's the major product in here? Well, I would recommend first you need to start thinking about what is an electron withdrawing group and what is an electron donating group. We know that carbonyls are electron withdrawing groups. This is something we know. And we know that these kind of alkoxy groups, you can call them ethers, whatever, are electron donating groups. Okay? So, why? Well, if you can do resonance, you can see that this group wants to donate and this group wants to withdraw. So in this case, it's most likely that you are going to get the chlorine on the para position from this guy. You may get the chlorine here, or the chlorine, sorry, not there. You may get the chlorine, the ortho position. You may get the chlorine either ortho position, but in this case, it's not really, we're not really sure. I mean, this kind of steric hindrance might not be favorable to the ortho position, so if I had to guess, major product probably would be in the para position. All right, let's do this problem together. So first off, you have 2 benzene rings. Which one is going to be the more activated one? That's the one you want. The more active one wants to react more. It's going to be this top right ring. We're going to start with this top right ring, and we're going to nitrate it. So where would where would this nitro group form on this benzene? Well, you have a position here that's para and ortho. You have a position here that's ortho and ortho. You have a position here, para and ortho. Now, if I had to guess, just because of sterics, I would probably put it right here. Because one, this methyl group is pretty small, insignificant kind of sterics, as we described previously. There's nothing in this region, and it's as far away from this guy as possible. And this is probably, there's a lot of sterics that go on there. Next, we're going to attach this chlorine. So where would this chlorine go? Well, it wouldn't be on this ring anymore. It would not be on this ring. It would go on this ring because this ring is too deactivated. That's what you need to be careful about. And this would probably, if I had to guess, would go in the pair position as well. Now this is a pretty good problem. So this judges whether you can think of both sterics and deactivation in one. Let's continue. All right, so starting from benzene, please make the following product using 4 carbons or less. So I'm trying to keep this as neat as possible, but it might get a little bit messy. So just looking at this, where do we even begin? That is the real question. Well, sometimes you might hear that going backwards is useful, and yes, it is, but you shouldn't go backwards the whole way, and you shouldn't go forwards the whole way unless you really know what you're doing. So going backwards is useful to see, okay, what's the last thing that's probably done here? Okay? Well, the last thing that's probably done here is this sort of acylation right here. So this acyl group attached here. We have at least one acylation in this ring. And how was this attached here? Probably another acylation. We have 2 acylations. And we have an alkylation, 1 alkylation. Question is, which one did we do first? Well, most likely, the one that was done first is this guy. Why? Well, if I put this group on, I can select for this attachment right here in the para position because of an isopropyl group. So I'm going to do that first. And then what most likely happened is we will use an anhydride because we have 1, 2, 3, and 4 carbons. So that anhydride will probably be the best choice in this sort of synthesis. All right, guys, well, let's just start. So I'm going to fan out this way first. So let's do alkylation. We're going to do Friedel-Crafts alkylation, not acylation, just alkylation. We're going to add this isopropyl group and add it to our benzene here. Okay, that's the first step. Next, since this is going to select for para, we can perform our acylation. So I'm going to be using the anhydride, and I highly recommend doing so as well. And this anhydride is going to give me, let me give myself a little more space. I'll just copy this since there's no need to draw it again. Anhydride is going to attach down here. So it's 4 carbons, 1, 2, actually let's give ourselves a little bit more space. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay. And I'm going to perform another, well, first, before I perform another acylation, well, if you realize if I perform another acylation, I'm going to simply form 2 carbonyls on this ring on the right. I'm going to form another carbonyl here, and I don't want that. So to avoid that, I need to use my zinc aluminum amalgam to get rid of that group on the right. So I'll start erasing things in a second, do not worry. So there we go. That's where we got to so far. So feel free to take a look at the synthesis, what we did so far, but I'm going to try to move things up a little bit more. Things a little nicer. Okay. All right, and then we use a reagent known as SOCl2. So if you remember SOCl2 from Orgo 1, SOCl2 is great with pyridine. is great at creating acyl chlorides from carboxylic acids. So I'm going to just copy this guy down here. And it's going to replace this with the chlorine. And finally, last but not least, we're going to perform our second acylation. All I'm going to use is AlCl3. And we get our final product. I'm going to just clean this up a bit and move this down, but hopefully that makes sense. Oh, sorry. Move this down. Okay. Hopefully that makes sense. So we started with our alkylation. Why did we do that? Because we want to lock in that pair position. After we get that pair position in, and we apply our anhydride, and we then have to use our zinc amalgam, get rid of one of the carbonyl in one. Another reason for doing that is we want it to be a weakly activating group, not the activating group, so we might screw up with the reaction. So we got to get rid of that carbonyl in one, and also because it's not in the final product. And even if we were just to make this a regular ring, we'd still have to get rid of it. And then we would just SOCl2 replace the alcohol and the carboxylic acid, and AlCl3 once more. So that intramolecular acylation. This is probably as difficult as it gets. All right, last but not least, we're going to make the following product starting from benzene. All right, how do we go about this? Well, first of all, you got to think of multiple pathways in your head. So let's start with, what if we nitrate first, right? If we nitrate first, if I add an NO3, right? What is that going to direct? Is that going to direct meta? It will. So are there any meta directors? Is there any groups meta to one another here? No. Right, so if I'm going to start with NO2, right, not NO3. Nitration, right? If I nitrate, it's going to give me meta. All right, now let's say, following line of thinking. All right, let's say if I turn this into an amine. Okay? Well, somehow I'm going to have to prevent this para position from being blocked. I have to block the para position. But when I put on the blocking group, I need to ensure that the blocking group doesn't go on the ortho, which means that this won't work either. So we're going to not nitrate first. What are we going to do? Well, there's only one other group on this ring, so let's start with that. First step, you're going to do your Friedel-Crafts alkylation. Add our chlorine. Second step, we're going to put on our protecting group. So I'm just going to write SO3H because the exact reagents in this case you can reference on your own. Now, we know that it's going to go into the para position, no problem. And why is that? Well, once again, in a para position, if you have something across from a activating group that's going to direct para, it needs to be, remember, smaller, like small, if you're going to get ortho-para mix. But if you want to lock in para, you need something large, kind of like an isopropyl group. So isopropyl group is perfect here. So we're going to block that para position. Then we are going to nitrate. So we're going to add NO3. And nitration will force it into the ortho. Then we can, these are interchangeable, we can H2PDC. And we can at the same time remove our, I'm just gonna do this in one step. We're gonna remove our blocking group with some H plus to form our final product. So line of thinking, nitrobenzene, think about it. Not gonna work if you start with making nitrobenzene and then going from there. That's why you gotta do your Friedel-Crafts alkylation first, form your isopropyl benzene, then add the blocking group to ensure that it's para. Then you add your NO2, And finally, you need to just remove the group and use palladium with hydrogen to ensure that it's an amine. All right, guys. Well, this is an extremely long video. We didn't expect it to be this long. I really hope that this has helped at least clear some misconceptions up. I hope to see you in the next video.